get started. So last time we introduced the notion of tangent space, tangent bundle, vector field flow, and at the end I talk about orientability. Let's see. So maybe strip. So maybe strip is non-orientable, one example. And then she asked a question good question about if you do the double cover. So for instance, if you rotate it twice, I think it becomes like this way. So this is indeed, you twist it twice in the middle, okay? So this is indeed, it becomes double cover of this one. Then, so one can find the nice coordinate transformation, whatever, the open patch and the coordinate transformation. A double cover, even though they're 2 times twisted, in fact, it can be orientable, even though they're 2 times twist. How to say? It twisted twice. In some sense, 180 degree once and twice, and 360 degree, it becomes orientable. And it can be, you can construct a double cover. It's double cover. Cover means the pre-image point of this map is something like whatever. There are 2 points, and each point, if you look at the pre-image of this map, so these 2 points are mapped to 1 point. That's double cover. And this is non-orientable. And this is orientable. And then I already forgot to ask a question. You or is a Gauss-Bonnet theorem applied to a non-orientable surface? That's the question somebody asked at the end of the lecture, and indeed this is the case. So since we can apply the Gauss-Bonnet theorem, which is chi of some kappa. This is Gauss curvature, or up to some constant kappa is the Ricci scalar curvature. So this can be applied for orientable surface, and since there is one can construct a double cover for non-orientable surface. So this is, let's go M tilde and M. So this M tilde, chi of M is also can be applied to. So the relation between them, since it's double cover, chi of M is 1/2 chi of M tilde. That's, you can easily think. So since this surface is double cover of the non-orientable surface, so this times 2 is equal to this one, okay? Since it's double cover. So for instance, Klein bottle can be just constructed, but opposite direction, unlike a torus. But if you take the two copy of crime bottle. It becomes torus. Okay, that's one way to see double cover for non-radial surface. And of course, it can be projected to the plane. And the plane, the curvature is just 0. I will explain later, but as you can easily imagine, there's no curvature on the plane. It's just flat. Okay, kappa is 0. So in both the case, or characteristic of Klein bottle is 1/2 of torus. And what is the oral characteristic torus? Speak out. 0. So therefore it's 0. Okay. 1/2 of 0 is just 0. So this is the one answer to the question at the end of the lecture last time. Any questions? Okay. So now, we introduce the tangent space at the point P on the manifold. This is tangent space. Space, which is a vector space. It's a vector space. As we learned last time, if there's a vector space, in general, if there's a vector space, one can construct the dual vector space. As we learned in linear algebra, so for instance, B star is the omega such that the B is mapped to, it's a linear map. It's a linear map from B to R such that, so it's a linear map. So this is linear map. Linear map means that the omega alpha 1 x1 plus alpha 2 x2 is equal to alpha 1 omega x1 plus alpha 2 omega x2, where alpha 1, alpha 2 are element in R, and x1 and x2 are element in B. Okay. So as you can easily see, so omega acts on x1 will give you real number. So it's a map from vector space to R. So this quantity itself R times R, element in R, multiplication makes sense, and you get some element in R. And in R, you can have also addition. So you have addition in two elements of R, you get the element of R. That's the element, the how you construct linear map. And to see this is a really vector space, so you just pick the two elements in the vector space, and then we need to show that the so this is also vector space, means that the if you pick two elements in omega in B star, which is which are omega 1, omega 2, then you just up to multiplication in element in R. So the linear combination of the two elements is also inside B star. So this is the meaning of vector space. Vector space. Vector space means you can have addition, just addition. Okay. So as you can easily see, given a two map on the B star, one can just construct B1 omega 1 plus B2 omega 2. So this is the element B star acts on X, okay? but X is an element in B now. And then you can just apply the map individually. So this is just operation. This is the dual vector space. This is what you learn, what you should have learned in the linear algebra. Okay. So now, since we have the tangent space at the point P in the manifold, which is the set of the tangent vector at the point P, but we want to, and which is a vector space. So therefore, we would like to. It's natural to think that what is a dual vector space. Okay. So the dual. So we just consider dual of vector space is cotangent. So this is tangent space, and dual is always include cotangent space. It's a dual to the tangent space. So in fact, given an element in it's a function. Let's consider function f, and then we can just have its differential df of p, such that it's a map of Tpn cross R goes to R. It's mapped to R, which is xp, is mapped to xpf. So in other words, dfp is a pairing. So as we know, so if you have an element in dual vector space and the element in vector space x, omega is element in dual vector space, x is an element of vector space, you can have a natural pair, okay? Because it's a map. That's how dual vector space is defined. So therefore, xp is indeed xp axion map. As we know, tangent vector is the map. Tangent vector map xp is a map of C infinity of M to R. That's what we learned last time, and it satisfies two conditions. What are the two conditions? Linearity and Leibniz rule. Good. Okay, so that's the tangent space is a map from C infinity of M to R. So therefore, given a function f, xp can act on f. Okay. And we define the differential df at the point P in such a way that its pairing will give you this one. Okay. And for instance, if you look at the local coordinate, so let's look at the local coordinate around the point P. At the point P, so there's a u is mapped to some phi. Phi is x1 xn, and it's a map in Rn. Okay. If you use local coordinate around the point P, the basis of this cotangent vector, basis of T star Pm is can be written x1 dot dxn at the point P. So remember that each local coordinate x1 to the each xi is a map from manifold to R, right? Each local coordinate is a map from manifold to R. Okay? So therefore, it's an element in C infinity of M. So xi is an element of C infinity of n. So one can define the differential, okay, like this way. Differential dx1, dx1, dxi, and then one can take the pairing between elements in cotangent space and then which acts on the element of tangent space. So as we have learned last time, first derivative with respect to local coordinate is a basis of the tangent space. And this will give you, as we can easily imagine, that this will give you that identity matrix. Okay, so that's, as you can easily see, so let's do step by step in that case. So by following the definition, df pairing of x is just pairing of this one, j of p acts on xi. So this is the definition. Now f is xi, okay? So derivative acts on xi only see when this derivative only see the function when j is equal to I. Okay? Otherwise you get 0. So therefore it becomes identity matrix. Any question so far? Okay. So this is how you define the cotangent vector. It's a very simple construction. So if you have a derivative, you have to. So when you learn derivative, you need to learn integral. Okay, it's like that way. So it's a very natural object we need to we are going to consider. And furthermore, so we introduce from the cotangent tangent bundle. I'm sorry. Still my brain is not working out. It's a collection of the tangent space. So now, so we consider this is a tangent bundle I introduced last time. So we can just consider similar consideration for cotangent space. And then we just consider T star of M as a collection of the cotangent space. This is cotangent bundle. So this is called cotangent bundle. It's a dual vector bundle. We will learn last time. And as we learn, it's similar to last time. I'm not going to go into detail. This is itself. You can introduce some topology, and this itself can be understood manifold of which dimension? What's the dimension of T star M? To n dimensional manifold. Okay. So, and then, yeah, I just want to write down some things. So last time, so we consider M and tangent bundle, and we consider section. So section. So section is called what? Section of tangent bundle is called what? Vector field. So tangent section of tangent bundle is called vector field, and we can just again the similar dual. Consider dual of things. T star M to N, and you can consider a section. Section section in the cotangent bundle. So X is called vector field. This is called vector field. Which just at each point you just assign tangent vector, and you just smoothly move tangent vector all over the manifold. That's the notion of the vector field. Now vector field, as we learned last time, is the first derivative, and we need to the quantity which can integrate as a dual space. Then the omega is called one form. So the dxi is a basis in terms of basis of this one form in terms of this local coordinate around the point P. Okay, and as I mentioned last time, so the x is an element of flux x of M, which is a section of tangent, which is the element of section, which is a section of the tangent bundle, and the omega, maybe I should write down like this way. The omega is so-called one form of M. So this is omega, capital omega standard notation one form. This is set of one form, which is a section. So as I mentioned last time, gamma is the standard notation for section. Good. Yep. And so given a function f over there, so one can just smoothly define this pairing in terms of p smoothly. So therefore, given the function f, you can define one form df. This is the element of omega. It's a one form. Okay, maybe I should write down like this. So f is the function, smooth function of manifold, and you can associate, just bring by one form in such a way that the df, natural pairing x, is just an f axon. And this is element of what? Oh, I'm sorry. I made a mistake. You should tell me. Yeah. Element of what? Good. So this is smooth function. Element. This is smooth function. Okay. So last time we learned that the vector field is a map from function to function. Okay. Since we smoothly assign the element in R all of the manifold M, which is the function over M. Okay, so this is the notion of the one form, and now we will learn one form. Okay, so now we would like to understand what's going to happen. So given us two manifolds, M and a manifold, yeah, both are manifold, smooth manifold. Then we construct some map from smooth map from M to N. Okay, and we'd like to understand how this map acts on. How does map operate on tangent at the vector field. Vector field in one form. So we like to understand. So this map induce the push forward of tangent space M to tangent space of M. So now what we are thinking about is manifold N is mapped to some other manifold N, and the point P is mapped to some point f of P. F of P. Okay. This point is mapped to some point here. Okay. And now, so we consider the tangent space at the point P on M, and we just consider tangent space at the point f of P on N, and this map induces the linear map. So as we learn, so these space are vector space. Okay. As a vector space, one can introduce the linear map, the notional linear map, and this is defined by f star. So let's take element xp. This is an element of this is called what? Tangent vector. Just speak out. So this element in tangent space is tangent vector at point P. Is mapped to element of tangent space at point f of P. So this itself is tangent vector on N at the point f of P. Therefore, tangent vector can act on function. So this function g, so we are considering function of either m or n. Which function we are thinking about? Just speak out. It's hard to distinguish m or n. N. Okay, so we are thinking about the function on n, because we are looking at the space on n. So g is a function on n. So this is equal to xp acts on g compose f. G compose f. G compose f. This is a function, as we learned. So g is a function on n, right? If you compose, this is f. M goes to n goes to r. If you compose f dot g, or I mean, function always acts f first and next g. Okay. So if you first act on f and then g, you get the function on n. If you compose it, if you have a function r from m to r, okay. Therefore, this is a function g compose f is function f. Oh, sorry. You should tell me if I make a mistake. Okay. So therefore, xp can act on the function on m. Okay. So this is the definition of push forward. So this is called push forward. The reason why it's called push forward is tangent space is push forward to n. Okay. As a linear map. Now, as you learn in linear algebra, if you have a push forward in vector space, now we would like to consider what's going to happen in the dual space. And as you can imagine that the so this map F induces push forward as a pullback curve one form. F star, which is cotangent space of n, goes to cotangent space of n. Now, what we are going to think is just consider a dual space. No longer it's a tangent space. If you consider dual space, F induces pullback. You just pull back, okay? Pull back of the cotangent space. This pullback is F star. So this is a dual space, and it's a natural construction of the, so given the element in omega, F of P is mapped to F star omega P. And now we can take a pairing. So this pairing between F star omega P and XP. Pairing. So it just, so this is the element in cotangent space on M, so you can just naturally pair with this XP. This XP. Which is equal to omega P. Oh, sorry, F. What I'm doing? F of P. F of P. So now we can have F of P, which is acts on F star XP. Okay? You understand? So F star XP is the element is tangent space on N, so therefore you can just have a natural pairing between tangent space and the cotangent space on N. Okay, in N. You can have a natural pairing here. Whereas if you look at the tangent space in M, so you can have a natural pairing with cotangent space. So that's a pairing here. And this should be equal. So that's a relation between push forward and the pullback. Okay, do you understand? So in other words, so in upstairs you have F star, TPM goes to TPM goes to TF of P of N. On the other hand, you have a dual space F of P star of N. This is push forward and pull back. And this is push forward and pull back. And you can have it's dual space, so you can have natural pairing. So you have natural pairing. As a dual vector space. Okay. Do you understand? Any questions so far? So far, it's a bit abstract, but I will give you the examples soon in the differential forms and so on. Okay. So now, so this, yeah.
It should be F star omega F.
F star.
The bottom line.
Which one?
The second line should be omega fp to f star omega ft.
Thank you very much. Thank you very much. Yeah, please tell me if I make a mistake. So, when you consider manifold, you always need to do something to understand the manifold. We also do the same thing in physics. Classically, all the field, scalar field function over M, manifold M, and then so we like to understand what's going on in this map. And for instance, if this push forward TPM goes to TF of P of N, so the push forward between time and space, if this is surjection, do you understand surjection? It's onto. Do you understand what it means? Surjection. Do you understand surjection? In other words, okay, so this is rank of F is dimension of N. So in other words, so this is a linear map. F star is a linear map. So the vector space to some vector space to have a linear map. You can always define. So if this is a linear map, let's call what is it called? Let's call it G. You can have rank of G. Okay, rank of G. It's a matrix. As a matrix. So if this is m dimension, this is a G can be understood m times n matrix. Okay. So if this is m dimension, this is n dimensional. So G can be understood as it depends on notation. So matrix which is, let's see, m depends on notation times n matrix, and you can have an element e1 en. So this is can be understood G. And you can always consider the rank of the matrix. I think you have learned in linear algebra, right? The rank. So if rank of the matrix is dimension of n, in this case, I assume dim of f is of course m, and dim of n is equal to n. So this is called surjection. Okay. If this is the case, f is called regular at point P. Otherwise, F is critical. P is critical point. of f. So in other words, for instance, we can consider the following height function. So given a definition and so on, always you need to consider the example. So this is a map from S2 to R. And I just consider height function. Let's go, it's H, stands for height. The height function, you just map a point to the whatever, x2 direction. I just consider x2 direction. So now we have, so we call it x0, x1, x2. And I just project to the x2 coordinate, everything x2 coordinate. The map point P, x0, x1, x2 is mapped to x2 coordinate. What is the critical point of this map? Speak out. Okay, good. So for instance, given a point here, you have a tangent space, and if you look at the height function, so it's a map, it's mapped to this point, okay? And as I mentioned last time, so the tangent space is a set of the tangent vector, and tangent vector is just that first derivative curve around here. Maybe I should use the yellow color, the curve. This curve is mapped to this curve, okay? So therefore, so this tangent space is mapped to tangent point at point P. This is h of P, okay? So this is TPM is mapped to, this point is TH of P of R, okay? So this two-dimensional vector space mapped to one-dimensional vector space. But as you can easily see, so this curve is mapped to the curve here. So therefore, it's onto. Two-dimensional is mapped to onto R, one dimension. So therefore, rank is 1. On the other hand, if you look at the North Pole and South Pole, it's just a tangent space is tangent to the North Pole. And if you look at the projection to R, it just projects to the point here, okay? So therefore, rank is 0. So as you can easily see, so that if you consider a curve that goes through the North Pole, it goes to like this way. You just go to the hit the highest point, they go back to here, okay? And if you look at the tangent space, at this point it's just 0, okay? Therefore, tangent space of this curve at this point is just 0. So therefore, this tangent space at the point North Pole is just projected to the point here. So therefore, rank is 0. The same thing happened here. This tangent space on South Pole is just mapped to point here. So rank is 0. The other point always have rank is 1. Okay. You can have the vector in x2 direction. Vector in x2 direction is mapped to always x2 direction in here. Okay. Therefore, rank is 1. Okay. So therefore, the point in the height function here is the sum. In this example, south, north, and the south pole. This is the height function, and the south pole R, critical point of high function h. Critical point of high function h. Okay, so that's the notion of the critical point and the regular point. And then, yeah. So the theorem of the third, I mean, this is very important theorem, but I'm going to omit, just state the theorem. The set of critical point is the measure. I mean, so measure 0 means that the measure 0 that the means that the, if inside R is just point. R2 you can have point or line. R3 if it is R3, so I'm just trying to R3 is a carry point, line or curve or whatever, or plane. But it doesn't. I mean, there is a precise definition for Lubeck measure 0, but I'm not going to introduce it. It's complicated, but you can just have a feeling of it. You can have feeling. So it doesn't, how does it fill the some subspace of R in the manifold. For instance, you cannot have something like a region. You cannot take like a region like this. This is no longer measure 0. For instance, in R2, if you have some domain in R2, this is no longer measure 0. You can have an area. In R3, if you have whatever domain or whatever inside of like a ball inside of R3, is no longer measure 0. So yellow one is not. Is counterexample of measure 0, okay? But in this point line plane inside of R3 does not have a volume inside of R3, so it's called measure 0. And the set of critical point in F is indeed the measure 0. So this is called third theorem. And the proof is given by very, very famous book by Milner. And this is very thin book. I think it's called Topology from Differential Viewpoint. Unfortunately, I missed the Miller's topology?
Topology from the differential viewpoint.
I mean, Milner's book is always a wonderful read for me, at least. And I think Milner's book is, I think, most read book in mathematics. This book is I think one of the most famous book in mathematics, and many students it's published, I think, in 1965. And you should know about this guy's name, John Milner. Yeah. He made a revolution in topology or differential topology. It's always good to read his book. For me, I highly recommend you at least take a look at it. And then it's a thin book, so you can go through. So, as you can easily see from this example, critical point is just point in north and south pole. Okay? North and south pole, it's just point. Therefore, it's just a north and south pole, so therefore it's just a measure 0. As you can see, it doesn't have a volume area. It doesn't have an area inside S2. Likewise, if you in general cases given a smooth map F and look at the critical point, the set of critical point is a measure 0. So it's a measure 0 means it's very something special going on at the critical point. So given R3, I pick a point here. It's a very special point. On the other hand, if you take some region in R3, this is not special. Okay, this is not special. And some particular point is very special. So therefore, critical point is very special point which can actually encode the information of this about this map, and also manifold between relation between M and N. So that's what third theorem tells us. So critical point is very special, and it encodes some information about this map the map from M to N. Okay, so let's move forward. Now we consider the surjection map between tangent space. What if injection? So if F star TPM TF of Pn is in injection for any point P, then F is called emergent. Moreover, if F is M goes to F of M inside N is homeomorphism. Oh, or diffeomorphism, sorry. I think I should call diffeomorphism. I didn't introduce the notion of homeomorphism yet, so that's why. Then, if moreover, then F is called embedding. Okay, so it's just a definition, and let's consider example. So for instance, Sn is mapped to Sm, where n is less than m in great circle. For instance, x0, xn is mapped to so this is actually indeed the embedding. So there is Sn is mapped to the great circle, equator. So this is Sm, and it's embedding to the equator Sn. Okay. So this is an example for embedding. As you can easily see, the tangent space at the point P here, is tangent space is just a line. I mean, I cannot draw the n-dimensional sphere, but if it is n is equal to 1, it's just a line. It's just line, tangent space. And if you look at the image of this point under this embedding, so it's the tangent space at point here is I cannot draw, it's m-dimensional. In this case, 2-dimensional in this figure. If m is 2, it's just 2-dimension. In general, m-dimension. But this line is mapped to here. So it's an injection. So TPSN is mapped to, by linear map, TF of P SM. So this is vector space, and this vector space, as you can easily see, this vector space is subspace of this tangent, the vector space here, okay? Subspace. Therefore, it's an injection. Okay? It's contained. Injection means contained. Okay? Subspace. And then furthermore, so this circle is diffeomorphic to this circle. Okay? The image is the same. Image is the same. So you cannot, you didn't have a like. For instance, one can also consider the following map. This Sn is mapped to all the point is mapped to the point North Pole. Let's consider such a map. Let's call this map embedding F as a map to the south point. Let's call G. Okay, G. As you can easily see, all the points are mapped to North Pole. So therefore, all the tangent space, all the curve is just mapped to a point here. So therefore, if you look at the if you look at the map G, push forward map G star, everything collapses to the point here. So it's an embedding. It's injection as a tangent space. However, the image is not the same as the original sphere. So sphere is not diffeomorphic to the point. Therefore, this G is not embedding. Okay, not embedding. Okay. As you embed, you just embed this sphere inside a bigger sphere as an original shape. That's what it means. Original topology. Okay. Original topology. That's what it means. Now we understand embedding. What is the immersion? Is there any example which is immersion but not embedding? That's we can consider the following pathological, or it's not pathological. Embedding. So let's consider the following. So let's consider another example of the embedding. Another example, S1 goes to torus T2. Okay. another embedding. So torus is, as I mentioned, torus is rectangle and identified edges. The edges are identified, where edges are identified. And we just consider that bunch of we just grew torus like this one. And now we consider the S1. So as I mentioned, this point is these points are identified, all identified, as I explained last time. And now we consider following line. And since this point identified with this point, okay? So therefore, at the end of the day, this green line becomes circle, okay? Therefore, this green line is embedding of S1 goes to T2. Do you understand? T2. Does anybody know this green line is called? Does anybody know this green line called? Do you know how it looks like? There's a torus. Torus here, and S1 is embedding. Let me use something. Let me cheat something to draw right figure. Does anybody not know this? So you should know, right? Do you know what's this called? You don't know, okay. You should know actually. You should know, but it's hard to draw. Sorry, I tried to copy from some internet how to draw, but and you should know what's the name. So this means that you just wrote it twice on it's called meridian, and 3 times in the longitude. It's called longitude. And at the end of the day, so I cannot draw the figure, but it becomes like this way. The figure and the torus is something like inside a torus. This is inside a torus, like this way. So as you can easily see, so they wrap twice. 1, 2, yeah. So it wrapped twice in longitude and 3 times in the meridian. Sorry, the other one. And this is called trefoil. Trefoil knot. So this is called trefoil knot. Yeah. And there must be some name in Chinese. Do you know how to write Chinese trefoil? Be careful about camera. Oh yeah, trefoil. Okay, thanks. So this is embedding. This is embedding. But however, one can consider, so this the reason why you can go back to the original point is that the so this you can go to 2 and you can go to 3 times of the grid. So it's a slope is, it's called slope is what? 2/3. I hope I'm not mistaken. So the slope of this line is 2/3. If this is a rational number, n/m. So if you consider some grid, if this is a rational number, at the end of the day, you just hit the point on the grid, right? So if the slope is rational number, you can have an embedding from S1 to T2. This is called n, m torus knot. It's knotted. S1 is knotted inside on the T2. It's knotted on a. So one of the examples, the simplest example. However, if this is not the rational number, slope is not rational number, it never hits the grid anyway. So it goes to. So if the grid is the slope is not rational number, if slope is not rational number, irrational. If it is irrational, so this slope is irrational. It's not irrational. It's irrational number. Give me an example of irrational number. Pi. Good. For instance, pi. Slope is pi. It never hits the point on the grid. Okay. So therefore, one can construct a map from this green line. Never hits the point on the grid. So therefore, this green line map is a map from R to T2. Okay. Then, if you look at the image of this map, so always given that, so this green line always like have image is something like a really dense. The image dense in the T2. As you can see, it just goes to infinity. Therefore, any point you take on a green line, you have something neighborhood. So any point, this is the image of this the map defined by this green line. So pick any point here and look at the open neighborhood. Open neighborhood, it always contains another line, which is the image of this map. Okay. So therefore, you cannot have if you look at the point here and look at the open neighborhood, open neighborhood. So you always contain another image. So therefore, it's not one-to-one. How to say? The gamma of t is no longer one-to-one map because of it contains. Sorry, it's one-to-one but not embedding. So sorry, it's one-to-one but embedding, not embedding because you cannot get a nice topology because if you consider open neighborhood, it always contains some other image. So therefore, it's no longer not embedding but immersion. It's immersion. So this is an example of immersion. Example immersion. So this is some bit strange example, but you have to distinguish embedding and immersion. Yeah. So any question so far? Okay, so this is a bit strange example because I mean once you take point here and you look at the open neighborhood, it always contains some another image point, so you cannot have a nice topology in the image. Therefore, there is no longer diffeomorphism. Okay, that's what happened for immersion. So I mean, so you can just have this example as to distinguish between immersion and embedding. So we can go a bit more. Okay. I think it's a bit boring to talk about the submersion and so on. So okay, I'm not going to talk about submersion. I don't think it plays an important role in this lecture. I mean, you can just read my lecture note about submersion instead of immersion. Okay. So now let's talk about differential form. We introduce one form, and we just consider a bunch of one form, and just try to consider the product. So we already know that given the manifold M, and point P, you can have local point nearby phi x1 xn local coordinate, and we know that the dx1 dxn is the basis of the one form on this open patch. And now we just consider algebra. So this is the basis. Let's see, P. Basis of cotangent space. Cotangent space. And we would like to consider some product between product. And now we just introduce the following product. So if you swap I and J, you get the minus sign. So this is called wedge product. So product means that it's just multiplication. And product, or in other words, multiplication. So, yeah. So it's a vector space. It's a vector space. We know that you have addition. It's a vector space, you can add something. But now we just introduce some multiplication in some special form. And if you swap the order, you get the minus sign. That's called wedge product. And then, so we just consider, if you consider so it's a vector space with multiplication. This is called exterior algebra. So what about this one? So if I and j are equal, what's going to happen?
0.
0. Why? Why? Why it's 0? Can you show?
You have something equal to the minus.
So this is equal to minus dx1, which dx1. So if you swap them, you get a minus sign. But they are same quantity. So it has to be 0 because minus sign. Okay. So this is exterior algebra. And then so this exterior algebra has a following decomposition. Often people just write down this algebra is and this exterior algebra has following decomposition. So where star k, t star p is spanned by dx I1, which total dx ik. It's spanned by these vectors.
Logo.
Oh, I'm sorry. It starts with k0. Sorry. If this is k goes 0, it's just function. So we now consider when k goes 0 part is considered. Yeah, I mean. Now it's just number. I think it's just number. It's number. It's just that k go part is isomorphic to some number. But let's see what it means. Some number. Let's see what it means. If we don't use local coordinate like dx local coordinate, so this k's power of the this which product is the actually the omega e side tk p star pm is define a map from k copy of tangent space to R. K copy in such a way that since element is just a vector tangent vector, so acts on omega is indeed since due to the property of the property of which product it satisfies this condition, where sigma is the element of a permutation group A. SK. Do you know permutation group? So 1, 2, 3, 4, K. And you just swap to some number, whatever. For instance, cyclic rotation can be something like this one. Right? Do you understand? This is or maybe you can just swap the some number. 2, 1, 3, 4, K. Sigma, if this sigma is this one, then sine of sigma is what? -1. This sine of is -1. Okay, if you swap two elements, you get the minus sign. If you swap twice two elements, you get another minus sign, and so on. So this is the how we act omega on the k copy of the tangent vector. And for instance, if you have omega, since this is k copy, so omega can be written as wedge product of k copy of one form. So omega I is the one form. Okay, omega I is a k copy of wedge product of one form. Wedge product of k copy of one form. And then this action can be understood as omega 1, omega x1 dot xk can be understood. So this can be understood definition. Wedge wedge omega k. Sorry, my choke is holder is not good. So omega k x1 dot xk. How it acts is you just consider the matrix so matrix, for instance, omega 1 x1 omega 2 omega 1 x2 dot omega 1 x k, and next element of omega 2 x1 omega 2 xk, and at the end of the day you have omega k x1 omega k xk. This is a matrix, and take determinant. This is how it, and then zero factorial. Sorry, I forgot the factorial. 1 over k factorial. So this is how the k form acts on the k copy of the vector field. Okay, so therefore more generally, I mean it's just a operation how the differential form. So this omega is called differential form. Acts on vector tangent vector. And more generally, it acts on, I mean, this is, I mean, as a physicist, it's very, very, very natural, and you already, some of you are already familiar with how it acts. X1. So omega is element of, and the eta is element of else, wedge product of M, xk plus L. That is how it acts, is 1 over k plus L factorial, and sum of a permutation group k plus L, and then sine of sigma. I mean, just how it acts. I mean, okay, and then times eta acts on sigma k plus 1. I mean, it's just a standard way to act on the differential form. As a physicist, it's very natural action. This is how you define which product acts on the copy of the tangent vector. Okay, So then we can just consider the smoothly of the vector field T star and Tk cotangent bundle is a union of all over the P wedge K T star P. Okay, so this is the wedge product of the cotangent bundle over M. And this also becomes a manifold. Should I tell you the dimension? It's a good exercise to find. Okay, exercise to find a dimension. This is manifold. You can introduce some topology and it becomes manifold. So it's a good exercise of dimension. What? Okay, so let's take a break, and then during the break you can consider you can fill out this one.
I didn't get it why the north and south poles are critical points. How can you prove it by definition? That the map is of rank. The rank of the map is just the dimension.
From the definition?
Because intuitively, it seems okay, but I'm quite confused how to prove it.
Okay. You can use local coordinate to yeah. How can I prove it? Let me think. It's actually there's a way to. Okay, let's do that. Let's do now. Where can I miss here? So, and it's just mapped to map with a high function. Let's take a look at the local coordinate around here, or whatever. Local coordinate, northern hemisphere. The local coordinate can be just a map to x0, x1. You just take the open patch as a north pole, northern hemisphere. Just northern hemisphere and just push to the disk, right? And then this map can be understood as 1 minus x0 square plus x1 square, right? And okay, let's take the derivative. So the time and space is also minus then d. So the simplified function dh at point dh can be understood as a minus right? And this becomes 0 when x0 x1 It is correct. Do you understand?
I get it.
Okay, let me get some. So, do you have a question? No? Okay, let me get some water. Okay, so let's resume. Oh, do you have a question? Does anyone have a question? Okay, so let's resume. So, what are the dimension? What are the dimension? Does anybody solve this problem exercise now? Huh? K? Just write down. Come here and write down. What are the dimensions? Come here and write down. Huh? It's okay, even if you make a mistake. Does anyone have other opinion? Other answer? Yeah. So there are two answers. Some other answer? As a manifold, what's the dimension of this case wedge product of the cotangent bundle? Always, it's some bundle, so always you need to consider it's manifold M and there is some fiber. And we know that this direction is whatever, it depends on notation. He used this M is an M-dimensional manifold, and the question is what is the dimension of fiber? What is the dimension of fiber? There's two answers. Are these correct or some other answer? Just come here and just write down. Good. Do you understand? I don't know. I mean, people write down MCK or choose K out of M. Is that what you mean? Do you understand? That's a dimension of fiber. If you look at the basis I have written down here, you need to pick kth element out of n, okay? And even if you shuffle the order, you just get sign only. They're same up to sign. Therefore, this is the right dimension. This is the correct dimension. So what is the dimension fiber of this one? The top form. It's called top form. It's a top form. What is the dimension of top form? Fiber dimension of fiber. Dimension of fiber of this top form. Top. Huh? What's this? No, what's this? I'm asking this. It's just one. Okay, unfortunately I have to erase these two out there. I mean, as you can see, top form, you only have the base is always this one, only this one. Okay? In my notation, anyway, it becomes any, but anyway. That's the only choice you can pick as a top form. Okay? Okay. So we will continue to learn differential form. Yeah. So these are, anyway, before going that, one. Let's see. Yeah, so the before going that, let me ask the how about homework 1? I already post homework 2 on the e-learning. And after we grade, we will give a solution, and you can ask the. So after 1 week, we will give you back all your homework, but after grading all of them, and give you back. And I will post solution. So if you haven't submit, I think it's better to do before like 1 week after. Within a 1 week. Anyway, homework 2 is posted. Anyway, so it's to get the notion of the differential geometry, it's better to solve the problem and look at the example. And the example, I always try to connect to physics. Nowadays, everything about manifold and topology, differential geometry now. So at this moment, but at the homework, I always try to connect to physics. And now homework 2, there's a problem that try to connect the vector field and quantum angular momentum, quantum mechanics. I will continue to do that in homework. So try to solve by yourself, or you can. I mean, there are many students, so you can discuss each other how to solve it. And if you have a question, you can always ask a question in the WeChat. If you cannot understand my answer from WeChat, we can meet each other. If you're a graduate student, you can just knock my office. Otherwise, we can set up time for meeting. So that's how our discourse proceeds. Yeah. So, any questions about how this course? And I'm really working on some intersection between physics and this differential geometry and topology. If you're undergrad student and still do not belong to any group, any professor, and are interested in this kind of stuff, you can always come to my group. Some of students are here. So if you're interested, just contact me. Anyway, so, but you should ask these are students in my group, and then you can, if you're interested in joining my group, you can just ask them how my group is like. Anyway, they may tell you how my group is like. how strict it is like. Anyway, as you can easily see from my homework, you can see that. Anyway, but I just want to, I hope you to see the connection between differential topology, differential geometry and topology, and physics through the homework and this lecture. Try to, try to make you, fluent about the relation between them. Okay, so let's proceed. So, lesson 1 hour. Lesson 1 hour. Let's see how much we can go. So, we now introduce the exterior product or wedge product of the cotangent bundle. And now, so let's look at so this is the this is the basis for the exterior product of the wedge product of the cotangent bundle. And let's do the coordinate transformation. So if you have coordinate transformation at the other open patch, and other open patch, other coordinate side, which is y1, yn. So now I assume dimension of M is n dimension. And look at this intersection. So intersection, you can have two bases. There's a type. In the so one basis, the other basis can be understood sum of J1 Jk such that d xi1 dot of d xik dy j1 dot dy jk dj1 dot dy jk. And this is called Jacobian again. Again Jacobian. Do you know how to obtain this Jacobian? Do you know how to obtain this Jacobian? Okay, then how should we? Right. As a matrix, yeah. Thank you very much. So it's determinant of this matrix. So this is, I mean, most of people are familiar with. If you learn the GR, if you learn GR, this is always appear as a coordinate transformation, this matrix. Anyway, so you should know about this matrix, and I mean, GR physics is just write down whatever. This is that's how they write, and this is a matrix and a peg determinant. So and now, so we have a bundle again. If you have a bundle, always you can always consider the section. You can always consider section, and let me erase. So section is again, it's called wedge K of T star M. And then, so we usually denote it, this is K form. So this is the set of K form, the set of K forms. So the section is always some map to the bundle. K forms, and then in particular, omega zero form. So if you just take the zero form, it's just a function. It's just a function. It's just function, and then I already introduced omega 1 is one form as a section of cotangent bundle, and the omega k is just generalization. So in locally, so if you use this local coordinate, so this omega can be always. I'm going to erase.
Sorry, I think I read it wrong. It should be start from I1, I2.
Sorry. So you mean I1, J1, J2, yeah, J1. Okay, so sorry, up to typo. This is correct. And if you use this local coordinate, so omega in element it's a section of the bundle. K form can be a local coordinate. It just can be written as some function which is x dx I1, which dx ik, where I1 ik. Okay, so this is the local expression. One can just write down local expression. Means this is the expression on this patch, this white patch, and then you can also consider the expression for yellow patch by using y coordinate. You just replace x and y, x to y, but you have a different function. Now you have a different function of y, and I'm not gonna write everything. J1, Jk. Yeah, Jk, but G and F are related to this Jacobian. Oh, at the intersection. Okay, and there's a lot of typo in the lecture note. So why local coordinate y is not there. So x should be replaced by y. Bx should be replaced by by. I will change later, and if you find a more typo, just let me know. Okay, so let's proceed. So let's proceed. So omega is element is just map from a k copy. So omega is element of is a k form. Is the bunch of oh, did I erase everything? Oh, no, I hope not. Seems like I erased. Yeah. So the map, so this is k linear map. K linear map. But alternating. So this alternating means that the alternating means that the if you have it's just what I have explained last time just previously x1 dot 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 xk, you get the sign of sigma is times omega x sigma 1. This is what alternating means. Oh my goodness, you should tell me it's something wrong. Okay, so this is the the kth linear map. So kth linear map, another linear means the omega alpha 1 x1 plus alpha let's see x1 y1 dot x2 dot xk is alpha 1 omega x1 x2 xk plus let's go alpha 2 omega y1 x2 xk. So that's what the linear means. For when alpha 1, alpha 2 are some number. Okay, so one can perform very, very nice operation. So this is very, very essential in physics and mathematics. Very important operation which you call exterior derivative. So this D is an important operation one can perform, which is differential. Okay. So this is called it's called exterior derivative which satisfy the following property. So the k form goes to k plus 1 form. So this ordered to exterior derivative. So it acts as, so for 1 omega, look at the how it acts on function, which is the just 0 form. So df, so f is the element of the function. Df acts on is x of f. So that's what we all have already learned almost. So to define the cotangent space, we just define the f of p acts on xp is xp of f. That's how we define the natural pairing between tangent vector and the one form, right? The one form at point P is a natural pairing, okay? That's what how we define. So we just smoothly, continuously move the point P on the manifold. Then this is very natural thing to consider. So this df is the element of what? It's a one form. So d acts on omega 0 to omega 1. F is mapped to df as a one form. Okay. So then one form can act on vector field. Okay, and you have a natural pairing, which is the vector field acts on function. Okay. So this is the element of what? Just speak out. What's this element? Just speak out. Yeah. So this is just function, some function. So as I mentioned, so this K form map bunch of vector field to function. Okay. And this is the second property is most important. d square is equal to 0, which map omega k to omega k plus 2. And 3 is with Leibniz rule. So d omega which either d omega which either plus minus 1 to the k omega which d either, where omega is in case form. So these three properties are satisfied for this experiment. So this exterior derivative enjoyed these three properties. So locally it's very, very, sorry. I think locally it's very, very natural operation. So let's look at how it acts, D. So locally it's very natural operation. So let's look at this example. In precisely speaking, it has the indices I1 dot ik. So locally, d omega can be understood as sum of df I1 dot ik. So this is one form, okay? F is some function, so therefore df is some one form. So if you take the wedge product, so this is the local expression for the exterior derivative. So d acts on the function and just take wedge product. Okay, it's a very simple operation. Locally, but if you don't use the local current, one can just define the d omega is just k plus 1 form. Therefore, one can ask to k plus 1 vector field. And the relation between omega and d omega can be understood as 1 over k plus 1 over k plus 1 sum of k plus 1 I equal to 1 I plus 1 xi omega x1 dot xi. So this hat means that you just omit this vector. Okay, vector field. So therefore, in total, you have a k copy of vector field. So therefore, this is k form can act on k copy of vector field. So it gives function. It gives function. So this gives function, and this vector field can act on function. Okay. Yeah. Then at the end of the day, you get the function, and you just multiply some sign. It just looks like complicated, but it's just this one. Try to say this one without coordinate transform, without local coordinate. And some additional pieces are required. -1 to the I plus j omega. So this is the bracket or commutator. And then x1, xi removed, xj removed, xk plus 1. So now let's look at what's going to happen. So here, so you have here, this commutator will give you one vector field. And at the end of the day, so the other is k minus 1 vector field. So because we omit 2 vector field out of k plus 1, so you have a k minus 1 plus 1 vector field. So in total, you have a k copy of vector field, and omega can act on k copy of vector, and you get a function. Okay. Okay, that's how the d omega acts on k plus 1 copy of vector field. That's how you can define. As a simple exercise, one can do the following. As a simple exercise, if you have given some definition or so on, let's try to apply the simplest setting. That's you should do every time. Let's look at the omega is just function. Okay. So let's look at the omega is just function. F omega is 0 form. So d omega acts on x. Okay. Can be understood as I mentioned over there. How does it work? So this is how it should act. So this acts on x of omega, right? That's how it acts. Then let's look at the right hand side. K is 0. So this is left hand side. This is left hand side. And right hand side is k equals 0. So this is so you can ignore this part because there is no two vector field. You can ignore this part, and then only look at this one. And when I equal to only one component, when I equal to 1, you don't have a sign, and x acts on. So right hand side x acts on omega. Nothing here, nothing. Okay, so k is 0 and 1 is omitted, so there are nothing. So therefore, right hand side is just the x acts on omega. It's a function. So therefore, left hand side and right hand side equal. So the for simple setting k equals 0 case is satisfied. And next, you just look at the k equal to 1 case. Let's write down k equal to 1 case. It's look like complicated, but you just look at each cases, then you understand. So let's look at k equal to 1 case. Omega is now one form of m. So the omega x1, x2 is, let's write down in omega 1, x2. So that's how it acts. So let's see. X1 omega x2. That's how it acts. X2 omega x1. Okay, and then you have plus. So this is 1 plus 2, right? So therefore you have a minus sign, and omega and then x1 and x2. That's how it acts. So now let's look at the coordinate in terms of coordinate. Let's look at the omega is something like a f. So it's a two form. One form x1. So x xi dxi. So this is the case. It's local coordinate to n. Then what you can do is the omega is something like a sum of dfi of x which dxi. Okay, I is equal to 1 to n. Okay, and then now we can apply the omega acts on some vector field. Let's take a simple setting. Let's take the very simple one. Let's see dx1 and x2. So let's take the simplest possible vector, two copy of vector field, and then let's look at how it acts. So now we only see. So this can be understood as something like a. What's relevant to us is so as we already written down. So dxi coupled with dxj. So this natural pairing will give delta ij. Okay. So what's relevant is that the component d omega I and bunch of vector. But what's relevant is only this part. Okay. Only this part. Plus dot dot dot. You can just ignore the other part. Only the basis, and we would like to know this part. Okay, do you understand? So let's take a look at. So then in this case you have df1. Let's see. And a bunch of stuff, but we ignore this part because it's irrelevant when you consider this pairing. Okay? So therefore, at the end, so this part can be written as, for instance, df2 dx1 minus df1 dx2, and then dx1 which dx2. It's just calculation. So then left hand side is something like you just have this one. Let's see, I hope I'm not mistaken. Is there any, now I'm worrying about the sum coefficient. Maybe 1/2 is involved, I think. Let's see. Yeah, I think it should be. It should be 1/2 should involved. I think 1/2 should be involved. I think let me try. I think this is question mark. I think question mark. I'm not careful about the sign, the coefficient. And this is left hand side, and let's apply this one to here. So this is left hand side. Left hand side. Left hand side is equal to this one. And let's look at right hand side. I think it's better not to erase here, so let me move on to here. A bit slow today, sorry. So right hand side. So now we know that the omega what was the right hand side? So here. So omega is 1/2. X1 is what? X1 is partial delta x1, and omega delta x2 minus delta x2 omega delta x1, and the commutator is 0. It's just I didn't consider any function here. If there is a function, you can you need to consider commutator, but I'm going to ignore due to for the sake of simplicity. This is right hand side, and now omega is written like this way. Okay, so we can just have natural pairing, which is 1/2. And natural pairing, you only see f2 of x that acts on partial x1 minus partial x2, and omega natural pairing only see f1 of x. Okay, this is the right hand side, and if you compare with left hand side, they're equal. Okay. So likewise, this complicated operation, it looks like a bit complicated, but if you use simple setting, you can understand what it means. Okay? Do you understand? So this f2 divided derivative x1, and so you can see left hand side and right hand side equal, right? So this definition just incorporate how this derivative, external derivative acts on this local coordinate, but in coordinate free way. So physicists like to always work on coordinate. Look, pick a local coordinate and just do a calculation. That's a physicist's way. Mathematicians don't like that way. Mathematicians just want to write everything into terms of coordinate free. Because manifold is there, and we just give some coordinate, local coordinate. A human being will give you a local coordinate. So, but manifold, what's happening in manifold is should be independent of the choice of the local coordinate. Okay. So therefore, mathematician always wants to write everything in terms of local coordinate free way, like this way. So the mathematician doesn't use dx, right? dx1 to the dxn. So here you just you have a differential form and a vector field. So that's it. We don't use any local coordinate. So but if you try to understand what it means, you always need to pick some local coordinate and do the calculation. Then you will understand what it means. Okay, so therefore, I mean, if you open the mathematics book, you have a bunch of definition, propositions, and so on in local coordinate free way. But if you try to understand, just use some example, use some local coordinate, and do the calculation. You will understand what it means. Okay, so let's move on. So, okay, so now we have so given a map, smooth map between two manifolds, we can again pull back our differential form in such a way that the case form to case form. So it's a pullback. Can you fill up this and this? Does anybody want to volunteer to fill out which manifold should be? It's a pullback. So this one is what? N and N. So it's a pullback. So differential can be pulled back from N to N. Okay, it's a pullback. Like what we saw in one form. It's an exterior product or wedge product of the one form. So yeah. And this can be defined as F star of omega acts on the case copy of vector field can be understood as just you just push forward the vector field and take. So here, so this pairing occurs on the manifold either M or N. Which one? Here, pairing on which manifold? M or N? Speak out. M or N? So just speak out, otherwise I cannot tell. Which manifold this natural pairing should take? It's pull back from N to M. F star just pull back differential from N to N. And take pairing with vector field on M. So this left hand side occurs on M. Whereas right hand side, original differential lives on manifold N. Okay? And x1 to xk lives on manifold M. But we just push forward vector field from M to N. Okay? Therefore, these vector fields are living on manifold N. Okay? And take pairing. So this is what's happening on N. But the body should be the same. Okay. So what I meant is the pick point P. So what point P, and the point F of P. So that's what we mean. This is a function, and you can take point P. You can pick point P. Then you have some value of function. You pick point F of P on a function on N, and they has to be equal. That's what it means. Okay. So. Okay, so then there are lots of property one can satisfy the push pullback. So one property, I'm going to just write down. So F star should be, this is very common. So this should be linear. So we are doing linear algebra, complicated linear algebra, bit more complicated linear algebra. So always has to be linear, and one can apply for each form. The pullback can be applied for each form. So omega of k, the k form, L form. If you take a wedge product, pullback should apply for each of the form, where this is the N and N. And furthermore, so if you compose the map, so this is a map. This is F and G. So one can just pull back. So the map F compose G. I don't know how is L. Then differential form omega k of L. So pullback is called contravariant. So pullback has to be applied. First, you pull back L to N by G star, and next you pull back the form from N to M. So you just compose G star and F star. Okay. So map is composed. First apply F, and next is G. F and G. Pull back is G star, F star. So this is called. It's better now. It's in mathematical language. It's called functor. It's contravariant functor. But anyway, I'm not gonna explain. What? Okay. So this is three property. 4 is the a commutative with external derivative. So, can anybody tell me something about how does D act on? How does this D act on? So this D should act on which manifold? M or N? Just speak out. I cannot tell with. I think it's better not to use M and N in this lecture. Unfortunately, I cannot tell which one. So this F star is the pullback, right? So before pullback, D should act on N. Okay. After pullback, this D should act on differential form on N. Okay. So, in other words, people usually write like this way. Mathematicians always write like this way. So this is differential. This is differential or external derivative. And pullback acts on like this way, and star. Okay. So this means that the d f star is equal to f star d. Okay. So f star d, left hand side is this part, and right hand side is this part. Okay. They should be equal, and the mathematician often write it's coming like this. Anyway, it means it doesn't matter how to go from one to the other. Okay, one to the other. It doesn't matter the path. Okay. So that's the how the property of differential form. And the reason why we introduce differential form is that instead of the vector field is the first derivative, and the differential form you can integrate. Okay, that's why we want to consider dual vector space. So the question is how to integrate. So if it is Rn, it's easy, right? If it is Rn, it's very easy. Given a differential form, like a function x1 by I1, ixk, x dx1, dxn, it's oh sorry. Yeah, I think I should write like this way, Rn. You already know how to integrate, okay, this function. So we know how to integrate over the Rn, okay? And so we know that the manifold M can have atlas. So it's defined by atlas, and it's mapped to Rn. And in some open subspace in Rn. So we know how to integrate in local current Rn. Okay? And we just want to patch together all over M. That's what we are going to do. So we have the open covering or atlas for manifold. And we want to integrate each patch, okay, differential form, by using local coordinate. Local coordinate here, local coordinate. And to do that, but you have to be careful about around this intersection. We don't want to double count, if you integral form here and integral form here, then you have to do the double count here. If you do the naive integral over two patches, you do integral twice over the intersection. Okay, so we want to avoid. To avoid that, we just introduce so-called partition of unity. Yeah, partition of unity. Partition of unity. So partition of unity is as follows. So you just have a U manifold M, and there's a open patch U and V, and then there's a 1. So now, so in the here, so this is B. Let's call B, and this is U. This is U, and you just divide 1 into smooth way. So at this point, let's use some other color. Let's see, blue, or some other open patch. But here, I have a 1. So there's a 1 here. So now you just put the support smooth function. Oh my goodness, I cannot draw nicely with this height. Sorry. So let's take it a bit lower. And I just want to write a bit more intersection. Otherwise, it's hard to draw the smooth function. Intersection is around here. So now, so I just take the smooth function smooth function, oh my goodness. Okay. No, I think it's okay. Smooth function. Sorry, it's hard to draw. Okay. And now, so this is what it means. So red and green, summation of red and green should be always 1. So if there is no overlap, it should be 1. But if there's an intersection, the body of green and the body of red, if you add them together, it should be 1. Okay? So at the intersection, 1 is divided by 2 support. That's what it means, in smooth way. Okay? That's called partition unity. So if you have in local patches and there's an intersection, just schematic. So intersection, if you have some partition with unity, like this way, and then here it's a partition with unity. So at the end of the day, so the summation of red and blue has to be 1 at the intersection. Okay? So then we can avoid the overcounting of integral around the intersection if you introduce partition of unity. Okay? So this partition of unity, so therefore, manifold M over omega can be understood as sum of alpha, chi alpha, this is chi alpha, of omega, U alpha, where U alpha, partition chi alpha associated to atlas of M. So this is how you perform the integral of differential form over the manifold. So chi alpha is the function. So this is chi. Essentially this is chi u, and this is chi v. Chi v. So you just multiply some weight, which is equal to 1 at the u without any intersection, but the intersection they divide 1 into u and b. That's how this partitional unity do. And this is how you integrate differential form over the manifold. So I will stop here, and next time I will recap a little bit about this, how to integrate the differential form the beginning of next time. But I hope you understand the meaning of the what it means. So any question? Yeah.
I have a question. The definition of exterior derivative, is this unique, or we can find another definition?
No, it's
also?
unique.
It's
Unique. Any other questions?
And I have tried to verify that D composite D is zero. And but I didn't make it. To verify the second property, the D composite D.
But you can do that. If you're, I mean, you just apply again D over here and D over here, D, everything D over here, and then you get that. Any other questions? Yeah.
I didn't understand omega on partial over partial x is f.
Which one? Okay, then let's finish, and then I will answer the question individually. So let's finish the class. So what so omega. And then omega x1 should be so this one acts on this one. So but I and if you take pairing I and 1, only one you keep it not trivial. You understand? So I exchange delta remember? Therefore, when I is equal to 1, it is only f1 or otherwise f1 dx1 non-trivial acts on this vector field. Otherwise, if it is 2, you get 0. You understand? You understand? So for instance, f2 x2 acts on partial x1. So if you take pairing between them, it's just that as we learn, so this is equal to f2x x2 x1. So this is 0, right? Therefore, if this is I except 1, you get 0. The only what's left is 0. Therefore, you get here f1 and then here f2. You understand? Okay. Left hand side?
Yes, what have
On top? Okay, so by definition, I think I already which products, for instance, dx1, which is x2, actual version x1, is x2. This is factorial, and then you just have to act on this one and this one. How should I say? This is equal to 1/2 by definition. Yeah, this is k factorial. So if it is k form, it should be k factorial.